Good morning, everyone. I know we've got a few people joining and will probably join as we go through. But I'd just like to welcome everyone to the first edition of our 2024 CEBRA webinar series, or as we like to call them, CEBRAnars. Probably should trademark that, shouldn't we, Andrew? For those that don't know, my name's Richard Kane. I'm the Principal Director of the Research and Innovation section in Biosecurity Strategy and Reform Division. I should say branch, not section. Before we begin, I'd just like to acknowledge, for me, it's the Ngunnawal people as the traditional custodians of the land on which we're meeting on, and recognise any other families with connections to the lands of the ACT and region. Also wish to acknowledge and respect their continuing culture and the contribution they make to the life of the city and the region. Noting we have a wide range of participants here, I would extend that recognition to the traditional custodians of all other lands on which our staff and participants are gathered here today, as well as to all Aboriginal and Torres Strait Islander people who have joined in for today's CEBRAnar. I just mentioned it before, but just as everyone's joining in, if you can mute your microphones and keep your cameras off. At the end of this dual presentation, there'll be the opportunity for questions and general comments. There is also the chat functionality as well. So if you've got any questions as it goes along, you can put it in there and we'll get to them at the very end. Or you can use the hand up function as well if you really want. We'll try and make sure we factor in for everyone. All right. For those that don't know, the Centre of Excellence for Biosecurity Risk Analysis, or CEBRA, is a long-standing biosecurity research initiative. Plays a vital role in providing Australia and New Zealand governments with expert biosecurity risk analysis and advice that helps inform a range of biosecurity risk management activities. Today, we are very lucky to have two of CEBRA's finest chief investigators. We have Dr. James Camac and Professor Tom Kompas, who will be presenting and discussing their work as part of the multi-year project Forecasting Trade and Biosecurity Risk under Climate Change. This project originally began in circa 2021 and has developed models aimed at improving government foresight into which global regions and economic sectors are most susceptible to changing climate, as well as how international trade flows may change as a result and what consequences this may have for biosecurity risk material hitting Australia and the borders of its trading partners. Both of our presenters are no strangers to the CEBRAnar scene, and it gives me great pleasure to introduce them. Dr. Camac is a Senior Research Fellow and Chief Investigator within CEBRA and Associate Editor for the Australian Journal of Botany. He's a trained quantitative and applied ecologist with extensive experience in field ecology, long-term ecological monitoring, experimental design, ecological statistics, reproducible data science, biosecurity risk analysis, and project management. I hope I named them all. I probably didn't get them all, so apologies. Professor Kompas is a Chief Investigator with CEBRA and a Professor in Environmental Economics and Biosecurity in the School of Biosciences and the School of Ecosystem and Forest Sciences at Uni of Melbourne. He's also a Fellow of the Academy of Social Sciences, Australia, Research Group Director for the Environmental and Economic Research at Uni of Melbourne. And also Foundational Director of the Australian Centre for Biosecurity, Environmental Economics at ANU, as well as a Distinguished Fellow of the Australasian Agricultural and Resource Economics Society. I think I got it all, but neither gentleman, as you know, without their fair share of accolades and awards. In addition, I also note that both of them were part of the CEBRA teaching team who received an Australian Biosecurity Award in 2022 under the education category for their biosecurity graduate course, and it was very pleasing to see them both there to accept that. But just before I do hand over to both of our CEBRA presenters, can I just take this opportunity to let everyone know that we are now advertising and the nominations are out for the next round of Biosecurity Awards. It should be out sometime this week and available on our website, on our biosecurity.gov.au. You can go and have a look there. Enough shameless advertising. I'm going to throw over to Professor Kompas first to present. I can see your screen. It's over to you. And then after that, we'll go to Dr. Camac and then questions after. Thank you.
Rich, thank you very much. And thanks to everyone for tuning in. We really appreciate it. As Rich said, this is sort of, in a sense, the close of what's called Project 21B. And we're very grateful to the department for supporting us in this project. And indeed, you can see on the screen, there are a number of people at DAF who in fact contributed, and with great thanks. Also note that it's not just Jimmy and I. There's a big team here at CEBRA that worked on this project, and you can see their names there. Really couldn't do it without them, to be sure. Rich gave a sort of good motivation already, but let me just backcast a bit. I mean, in a nutshell, what we're doing in this project is asking the question, what's the impact of changes in trade patterns? What if imports and exports change for some reason? What's the impact? And we do it potentially across 140 different countries and 60 different commodity groups. So we're looking at a fairly complicated, large dimensional setting where we're asking the question, what happens if imports and exports change across the world and in terms of impacts on Australia? And then taking that info, well, I should say before I move on, we're going to focus on climate change today, global warming impacts today, with an albeit limited set of damage functions. But the GTAP model framework, the trade model framework we use, can be used in a number of different contexts. Changes in trade patterns or trade agreements, TTP. Donald Trump comes to office, Ukraine war continues. All these things can be done and modeled in a fairly nice way in terms of changes in trade patterns in the GTAP framework, what we're calling a GTAP model. And indeed, we use a GTAP model since a well-established database that comes out of Purdue, Indiana. So we look at changes in trade, focusing on climate change in this presentation and the damages that accrue from climate change, and then ask the question, what's the changes in pest pathways as a result of the changes in trade, imports in particular into Australia? The pest pathways are conditioned by layers for host and climate suitability, population layers, and so on, and Jimmy will highlight that quite nicely. And that's it, basically. We're trying to be proactive. We're trying to ask the question, what would be the changes in pest pathways or pest entries into Australia as a result of these changes in imports and exports around the world, given different kinds of impacts, in particular changes in global warming? And that's it in a nutshell. So let me start flipping the slides. So the motivation is quite clear. I borrowed this from one of Jimmy's biosecurity common slides. You know, biosecurity risk is increasing globally. We know that. And there's all kinds of good examples on this slide that indicate that. There's increasing trade, and indeed, again, changes in trade patterns, which is important for us. There's changes in species distribution as a result of global warming and other impacts that are relevant to talk about. And indeed, there's global human movement. And indeed, one of the key elements that's missing from this work in 21B is the effect of changes in tourism. We haven't included that yet. We know how to do it, and we've got the data for it, so it'd be a really nice extension. At the moment, it's just focusing on changes in exports and imports across commodity sectors or groups. So tourism left outside the picture at the moment. But biosecurity risk is increasing globally. So we want to find a way to be a bit proactive to try and determine what might happen in terms of establishment exposure, given changes in trade from things like climate change or other global trade patterns that are in fact evolving over time. All of this is to, in a sense, to better inform border screening and indeed post-border surveillance for that matter. So here's a nice graphic we prepared that sort of describes what we're doing. And how the models sort of fit together. For Jimmy and I, this is a really great project because we were able to combine our two favorite models together into one integrated framework. The material in yellow is the climate change modeling and the trade modeling that goes with GTAP. So it's, you know, looking at the changes in exports and imports as a result of climate change damages going forward. This is the material that sort of I work on, Matthew Cantelli works on, Christine Lee works on. We're trying to, in fact, incorporate damages from climate change into changing trade patterns. That's the yellow section. The blue section, that is Jimmy's work, right? Where you look at changes in species distribution, you look at all kinds of layers, climate and human layers and host suitability and so on. And you try and determine what the change in pest pathways would be, given imports at the border for Australia, given changes in trade patterns. So I'm focusing on the yellow, and I'm going to try and leave plenty of time for Jimmy to focus on the blue. But they go together, and that's what's really cool for us, because this is a way in which we could combine the works that we were doing in a very innovative fashion. I'm quite happy with it. So, climate change. Everyone here, I think, will know that temperatures globally are rising. These are the patterns recently. Important to emphasize one point here. The black line is increases in global temperature that's normally reported. Going forward, it's the average across both land and ocean. Albeit most of our damages in the climate change model for the trade impacts are actually land-based damages. And indeed, land-based temperatures are increasing more rapidly than the global average. So it's good to keep that in mind. But, you know, there's serious issues here. And in fact, annual global temperature is now 1.48. So it's getting close to the 1.5 threshold in the Paris Agreement. The model is a very complicated graphic, and I don't want to go through all of it. The model is really, it's complicated. It's easy to understand, it's intuitive, but it's complicated dimensionally because it's 140 different countries, potentially 60 different commodity groups, and there's a number of plugins into this trade model out of GTAP. The key plugins, of course, are the way in which we actually form the model to capture the data and use the data in GTAP. But there's also all kinds of other sort of elements. There's a version of what's called Magic C, which sort of maps radioactive forcing into temperature profiles over time. For us today, it's basically just temperature profiles relative to RCP. You know, how quickly is the temperature rising from today up to 2100? We also, and this is important, include damage functions, right, from climate change. And the key ones we use at the moment are losses in agricultural productivity and heat stress impacts on labor productivity. Basically, it's a heat stress model. So the damages we're going to show you that result in changes in trade patterns are at the moment still relatively limited. We're working very hard to get sea level rise and storm surge layers into the model. And in fact, we're very close to doing that. But we're missing all kinds of other things. Losses in biodiversity, human health effects, bushfires, all kinds of things are still missing. And indeed, that's one of our aims in the future, is to try and build in more damages into this particular model. So keep in mind, even though the results here show fairly substantial economic losses, the damages are still fairly limited. There's some limited sea level rise in these estimations that come from a paper by Rozan and Satori, but they're very limited indeed. And indeed, I should note that the heat stress impacts come from work that Christine Lee has done with a group here at CEBRA, which has now been revised and resubmit actually its scientific report. So that's included as well. But it's basically easy to understand. You have a set of inputs. You have labor, land, capital, investment goods, some natural resources, and some intermediate goods. And you combine these in a GTAP trade and climate model to produce output. Some of the output is consumer goods and some of it's investment goods. And there are sectors. There's a household sector, there's a government sector, and there's an industry sector. So you're using inputs to map to output. That output could be consumed domestically, either as, again, consumption goods or investment goods, or it can be traded internationally in terms of a pattern of exports. And this happens in every individual country across the data set. 21B is calibrated for 60 countries and regions, but it can go up to 140 different countries. And indeed, it's done at annual time steps, or at least in principle done at annual time steps. So you can keep track of what's going on year after year, although the results I show you are generally going to focus on 2100. Because it's just typical to do that in climate change modeling. But again, annual time step. So it's that sort of approach, inputs to outputs with climate change damage functions, temperature pathways, right? And some additional material, some modeling material that in fact allows the model to run properly. So it's not hard to understand, but the set of equations and unknowns are substantially large. They're really large. to try and get this to work computationally. Here, just an example of the commodity groups that are used, and you can see it covers a wide variety of things. A lot of agriculture. In fact, GTAP was initially set up as an agricultural module in trade globally, but now a lot of other things as well. Manufacturing goods. It also includes oil and gas and renewables, all kinds of things that we eat and use. So it's fairly extensive in that sense. It's got all kinds of things. Again, it's now up to 60 different commodity groups, 57 when I made this slide. So you're looking at the production of these commodities. These commodities are consumed domestically or traded overseas. There's a pattern of exports and imports, right? You can consume foreign goods, imports, or export. You're asking the question then, if we have damages from climate change, what's the impact? In particular on GDP for individual countries, and hence, what's the impact on their trade, on their pattern of exports and imports? A little bit of indication of how severe some of these damages could be. This is from an earlier version of what Christine Lee and I did to look at the impact of heat stress on agricultural productivity across 4 crops for, in this case, the largest producers. And you can see there at RCP 8.5, which is the fairly dramatic increase in temperatures up to 3.8 degrees by 2100, the losses are substantial. Wheat in India, 21% loss. Maize in China, 24% loss. You can see if this was a food security presentation, we'd focus on this at length because there's serious issues here going forward depending upon the temperature pathway. The losses are still fairly large at 4.5 and 2.6, which is about a 2-degree warming, which is what we're headed for anyway. You can still get fairly major losses. So again, part of the damages in this approach are on agricultural productivity, but there's also heat stress damages on labor productivity, in particular for people who work outside in agriculture and manufacturing and construction. Those are also included. So if you pull all of this model context together, this framework together, and run results, what you get is, I'll show you a graphic now that some of you have probably seen before from me. It's the results for global economic damages from, again, losses in agriculture and labor productivity in 2100. These are heat stress impacts only, with some very limited sea level rise. One qualifier, Greenland is pink because it's picking up island states and other countries that don't have resolution in the global map. And of course, darker red is worse. So these are percentage changes in annual incomes in countries as a result of these economic damages from global warming. And they range from 1% loss to 28% loss. And you can see Africa, in particular Western Africa, but big parts of Southeast Asia, South Asia, Latin America, China, even Australia is a little bit pink here. Again, we're not including sea level rise and storm surge and other impacts that would more severely affect a place like Australia. But the point for me is you can see the heterogeneity in this pattern, right? It differs considerably across the world. The impacts are quite different across the world. And that tells you there'll be changes in trade, imports, and exports as a result of these changes in incomes. Early climate change modeling from economists was very, very inadequate. It tended to look at a small number of regions and tended to average across those regions. You miss the heterogeneity and you miss the whole story. Yeah, the averaging, in fact, is really problematic when it comes to looking at these impacts of global warming. If you look at the dollar cumulative losses from now until 2100, they actually do add up. They're about 610 trillion. This is assuming no further increase in population or economic growth, which might, in fact, offset some of these losses. But at 610 trillion, even with these limited damage functions, on average over 80 years, it's about 7.6 trillion per year. It's about a COVID-sized shock each year for 80 years, for each one of the 80 years on average. Of course, with climate change, it's backloaded, so most of the damages accrue later, but the average is a tell. All of this has been peer reviewed and published in 2 journals, Earth's Future and Nature Climate Change, so you can check it out there. But what we want to focus on now is the change in trading patterns. And indeed, you can see what happens. This is a nice little graphic showing income on the horizontal axis and losses in GDP on the vertical axis, where the size of the circle is an indication of population. You can see how the distribution is slanted in terms of damages to low-income countries. Most of those countries, in fact, export agricultural and other manufacturing goods, so it's good to keep that in mind. But you can see India, big circle, China, big circle, countries like Australia and the USA, less impact with these limited damage functions, and indeed income levels far above mean per capita. So it's really, sort of altering the distribution of damages weighted towards more low-income countries. That's clear. Again, with these limited damage functions, which will tell you something again about the pattern of imports and exports. So it's easy for us now. We got changes in GDP. We can map those changes in GDP into changes in trade, exports and imports. Some countries won't be able to export the goods and services they currently do because of these climate change impacts. Heat stress and labor stress will, in fact, imply less agricultural production out of Southeast Asia, for example, and maybe changes in manufacturing goods as well. And we can track that. That's what's great about GTAP, because it's so large dimensional. It's looking at all these countries and their interacting trade patterns. And if you do that, you can see what would happen. You can see the changes in trade patterns into Australia as a result of global warming effects. This is again at 2100. Keep in mind that we can do this at annual time steps. Don't actually have to think just about 2100. But I want to be a little bit dramatic. So let's have a look. These are the top 20 exporters into Australia. A bit hard to see this at first glance, but red means there's a decline in imports into Australia, and blue an increase in imports into Australia, where the thickness of the line is a measure of volume. You can see there's a shifting pattern away from Southeast Asia, China, and India, more towards Europe as a result of the global warming impacts. And if you drill down in this model, you can actually see quite clearly why that's the case. It's basically falls in income, generally speaking, that generate the change in trade patterns. There are also significant changes in exports from Australia to the rest of the world, which industry might want to be, sort of keen to see, because they do change dramatically as well. Here's the pattern for New Zealand, right? Sort of similar. But big changes in imports from Australia to New Zealand, which when we present this in New Zealand, sometimes is a bit of an alarm bell for them to make sure that no pests and diseases from Australia enter their country, I guess. But you can see fairly dramatic changes in trade patterns. And these changes in trade patterns allow you to sort of predict what the pest pathways would be from source countries for individual pests and diseases. Quite nice that way. And indeed, to wrap it up, and I'll give Jimmy some time, we've got an interactive dashboard that you can access, where you can plug in the country, select the importer, the specific commodity you care about. And here's an example. The importer is Australia. I looked at Italy. It's electronic equipment, and I looked at RCP 8.5. That's the high temperature scenario. And you can select the year, annual time step, so from 2014 forward. And you can see what the change in trade patterns would be, who the major importers are, exporters are, what the impact is on Australia as a result of having global sort of climate change damages. So I'll leave it there. And thank you for listening. This is my favorite graphic for climate change, right? I used to work on COVID modeling as well, and we wanted to squash the curve, lower the curve from the COVID effect. But the big one's potentially coming behind us. We've got to really keep it in mind. Jimmy, over to you.
Awesome. Okay. I've jumped a slide. So Tom's provided a really nice summary of the underlying trade model. Now, we all know that trade in particular, right, is a major pathway of pest entry in this into Australia, but also other countries, which can then lead to establishment. And so when Tom and I were working in the same office, and I'm working more thinking about pest risk and establishment coming into the country, and Tom's working on these trade models, we thought, wow, these two slot so nicely together. And particularly because we need to become more proactive as a biosecurity system. As Tom highlighted, risk is increasing. It's continuing to increase. We don't have unlimited resources. There's finite resources. And so we need to be smarter and more proactive, less reactionary. Right? We need to be able to predict what the future risk is likely to be. And so what I'll be talking about is basically how we integrated the ecological submodel, so the blue box here, with the trade model. And broadly, what it involved is Tom's model ultimately gives you some measure of what's the export volume from, say, infected countries into Australia or other trading partners. And we can link that to some of the underlying biological processes. So thinking about the climate suitability of a species, how that'll change, what we know about the contamination rates hitting Australia's border, and between the combination of changing climate, changing trade, and what we know about the contamination rates, what's that going to mean in terms of the propagal pressure or the number of contaminated items hitting Australia's border, and ultimately, what does that mean as a measure of establishment exposure by thinking about where does a pest, a contaminated item containing a pest, likely to arrive, and whether the climate in this case is likely suitable for it to establish. And so we're really trying to build in all this complexity, both in terms of the underlying economics and the underlying biology, into a holistic model that tries to approximate and forecast biosecurity risk. So how did we do it? Well, the case studies that we did for the department selected 5 case studies. They were broadly aligned with different functional groups of hitchhiker pests. They included spongy moth, Asian honeybee, giant African snail, capra beetle, and brown marmorated stink bug. Today, I'm only going to present some of the key findings for brown marmorated stink bug, mostly because it's the pest that's been most intercepted at the border. It's highly polyphagous, it's an environmental pest, it's an agricultural pest, and it's a nuisance pest as well. So that's the key one I'll be focusing on. So the first component of the biological or ecological model is thinking about climate suitability. Now, there's many different methods to estimate the climate suitability of the species. I won't go into them. Other than to say that we used a range bagging presence only method. I've actually advocated for this method in previous presentations for thinking about doing national risk mapping. So it's a method that has been used before. In this particular case, because we're interested in climate change projections, and in fact, under 2 different climate change scenarios, RCP 4.5, which is the medium-term average climate scenario, and the worst-case scenario, RCP 8.5. So what we did is there's many different types of models. They're called global circulation models, or GCM. So there's different models that estimates and projects how climate's going to change into the future. And rather than rely on a single model for the different climate scenarios, we decided to use as many as we could get. And in this case, we had 23 different global circulation models. And what we did is for each of those circulation GCM models is we made a prediction to climate on an annual time basis for each of them. So in the end, there was 1,978 predictions or global prediction maps that we produced per climate scenario, or GCM, per threat. And then what we did is then we can calculate the mean climate suitability for a given year, for a given climate scenario, and also quantify some of its uncertainty. And so what you see on the left-hand side here is just some snapshots in time for brown marmorated stink bug climate suitability. So the yellow warmer colours are higher suitability, and so the top map is basically the climate suitability in 2020, And as you can see, it will go to 2050 and then 2100. And some of the key things you want to point out is around Europe, we're seeing some slight declines in climate suitability, as well as parts of America. But you're also seeing expanding or increasing climate suitability in Russia and Canada. If you focus on just Australia, you know, currently climate suitability for brown marmorated stink bug is largely centralized around the eastern coast. And as you can see, as we progress from 2020 to 2050 and then 2100, it decreases and becomes more constrained to the coastal coast. Why do we need climate suitability? Well, it can be useful for two fundamental components in the ecological biosecurity risk model. It can inform how prevalent or how much area is suitable in the infected exporter regions. And therefore, it can also tell you something about what's the potential for the pests to be to hitchhike on different goods. So if a country's got a large area of climate suitability, they're more likely to be exported goods from that country are more likely to be exposed to the pest. And as a consequence, that's going to have impacts on the contamination rates coming from that country. So it can be useful for thinking about how does climate interact with contamination rates in terms of what's the risk leaving that country to going to other countries. But it's also useful for thinking about the risk coming into a country. So for example, Australia, just because we're getting propagular pressure or contaminated items hitting the country's border doesn't necessarily mean it's going to establish. That's where you need to think about the suitability of the environment, climate being a key factor in that. So how did we estimate contamination rates? Well, this has been a long time coming. I've done a previous CEBRAnar on the brown marmorated stink bug where we did some preliminary modelling using border interception data. But since then, we've got a lot more data, and the data has been continually refined and cleaned up by the department. But basically what we had is annual border interception data from 2014 to 2021, and that was identified down to commodity type and country of origin. In addition to that, we also had annual import statistics. And by that, I mean total number of imported lines entering Australia, as well as the number of imported lines that were inspected at the border, acknowledging that we don't do 100% inspection of everything that comes in. Again, this was broken down by commodity and country. We also had some information about which countries had known established populations of these different threats. And some of that came from the department, some of that came from CABI databases. And of course, as I've pointed out before, we've got these annual maps of climate suitability across the globe. So we also know what the mean climate suitability is for different regions and countries. And without getting too bogged down into the underlying math, effectively what we did is we built a statistical model. For those that are interested, it was a Bayesian generalized linear mixed effects model. And the main thing you need to know about here is that we included the climate suitability or the mean climate suitability in the infected exporting country. And we also included random effect terms for country, commodity type, and year. The whole point of including random effect terms is that they can account for effects that are otherwise not accounted for by just climate suitability of the infected country. But they also have some niceties about them in the sense that they can account for non-independence in the sampling. So countries that export certain goods might just have, you know, the contamination rate might just be higher in general for those. So there's non-independence there, or differences among years. Some years might be higher versus others. But the most important thing about a random effect in this case is it allows us to make predictions to unobserved groups. For example, we want to be able to predict into the future, so unobserved years. But we also want to account for the uncertainty that is going to occur, because there is going to be ups and downs in terms of contamination rates within years. And I'll highlight this, particularly the case with brown marmorated stink bug a little later. The one thing I just want to stress here, though, is that these contamination rates are almost certainly going to be on the conservative side. So they're probably going to be a lot lower than what's actually the true contamination rate. And that's because we can only model what we're seeing at the border. So effectively, we're assuming perfect detection at the border. Now, that's unlikely to be the case. No surveillance system globally has 100% perfect detection. We also we're also assuming that what we're seeing in the border interception data is representative. But that may not be the case. There may be certain things where we're not taking a random true representation of the contaminations that we're seeing at the border. And lastly, because we didn't know anything about how contaminated an item was, it could have been a single bug, right? And it could have been dead for all we know, right? It doesn't account for the viability. So this is purely, is it contaminated? Is it not? Not how contaminated it is or how viable it is. So what did we find? So these are, I'm just going to go through a couple of outputs that we've got from the contamination model. All right. And so what you're seeing here is effectively the average contamination rates for infected exporters, which is the panel A or the left-hand side, and panel B is the different commodity types that GTAP model models. So the main thing to take away from this figure is that at the bottom of the figure, that's the higher risk commodity or exporters type. So in panel A, you're seeing Italy and the United States being considerably more, having higher on average contamination rates relative to, say, Taiwan and Korea. Right. On the panel B side, we can see that petroleum and coal products, mineral products and motor vehicles and electronic equipment have higher contamination rates relative to sugarcane and processed rice and food, other food products. So straight away, we can get a relative ranking of what's the average contamination rates after accounting for climate suitability and the volumes of goods that are being exported. So these are probabilities of a consignment, whether of a general consignment in terms of panel A or of a particular type of commodity in panel B. We can also look at how contamination rates on average vary across years. And so this one's particularly interesting for brown marmorated stink bug because what we're seeing is that between 2014 and 2016, the contamination rates were on average lower relative to 2018 and 2021. Now, there could be many reasons to explain this. There's been policy changes in terms of what's been done at the border. There could be changes in inspection methods, but there could also be related to actual increases in populations within these countries, which has ultimately led to higher contamination rates. We can't tease that apart because we don't have the data, but that's something that we can continually refine as we continually get more predictive data that can go into these models. So as a broad outcome, what you get is contamination rates by commodity, by exporter. And on top of that, we can then, because we're accounting for climate suitability within the infected regions, we can see how that changes over time. And so what I'm showing in this table here is really what's the top 20 exporter by commodity highest risk contaminated items. And in this case, you're seeing a lot of ITA, which is Italy. So Italy is continually coming up as very high in terms of its relative risk. And if we go back here, Italy also comes out very high, right? So the models, this is just propagating the uncertainty and the effects through the model. And what you're seeing is Italy is coming up. And again, the same with the commodities. So we're seeing petroleum and coal products, so the P_C, minerals, motor vehicles, MVO, electronic equipment. They're continually coming up as the highest risk commodity types. And what you're also seeing if you go across the columns is that we can see that there's marginal reduction in the per line contamination rates. Right, so it goes from 3.1 to the power of -2 in 2023, and under RCP 8.5, so the last column, it drops down to 2.4 to the power of -2. Now, why is this? Well, this is largely driven by climate suitability in Italy decreasing over time, particularly under the worst case scenario, 8.5, which means there's less suitable habitat in that area. So now we've got a contamination rate model, that statistical model, and now we can link it to what Tom's done, right, which is the import trade flows. And basically, the two can give us a country level or regional level estimate of what I call propical pressure. But broadly, it's just the number of contaminated lines hitting the country's border. And that can be broken down by exporter and commodity. So that's all good. Right? That tells us something about what's the risk hitting the country's border. But as I pointed out before, just because something hits the border doesn't mean it's going to establish. So what we can also do is think about a relative measure of establishment exposure. And in this case, you've got to think about how the imported goods that might contain the pest are likely to be distributed across the space. And luckily, as we were doing this project, there was some recent work published where they actually modeled changes in human population on an annual timestamp under many different climate change scenarios, and produced high resolution 1 kilometre rasters globally of human population. So we harnessed that data, right, and then basically allowed to see how the human population changed geographically, so in space, over time, and we used human population as a means for dispersing that country level propical pressure hitting the country's border. And by doing that, we're making the assumption that imported goods are going where the demand is greatest. And in this case, we're assuming demand is greatest by where people are. And then, so that tells us something about where those goods are potentially contaminated goods are going. And then basically from there, we can use the climate suitability model for Australia to go, well, is it climatically suitable? And so we can weight it that way. And that gives us the bottom diagram here, a measure of establishment exposure. And if we want to, we can then aggregate that up to get a country level estimate. And this is basically what we end up with. We get a propical pressure a model, so that's the prediction, which is the left panel, and then we get an establishment exposure panel, which is on the right. Now, there's a couple of things to quickly point out here. First, there is high uncertainty. There's high uncertainty because we've got many, many different types of commodities coming from many, many different countries. And when we actually use these contamination likelihoods and multiply them effectively by the number of exports, right? Small likelihoods that are, a little bit uncertain, multiplied by many, many numbers of exports, ultimately result in larger uncertainty bounds around it. So that's the first thing. But the other thing to point out here is, as you can see, there's the red line, which is the medium climate change scenario, and the blue line, which is the worst case climate change scenario as projected at the moment. And you're like, oh, there's a marginal reduction for the worst case scenario, but not huge, right? And the question is why? Well, part of the reason is that most of the hitchhiking threats, particularly for brown marmorated stink bug, are coming on manufactured goods. Now, manufacturing, as Tom pointed out before, is partially impacted by heat stress and impacts on labour productivity, but it's marginal. There are other damage functions that we need to include in the model to better encapsulate what the climate change impacts would be on manufacturing. One of the most notable being sea level rise, given that a lot of manufacturing is done near the coast. The other thing to take away from this is that there is compensatory effects going on. So declines in trade in one country might be offset by increases in trades or increases in contamination rates from another country, because that's what's going to happen. We're going to still have demand for electronic equipment. It's just going to come from a different place. And that country may have the pest. And in this case, the brown marmorated stink bug, a lot of our major trading partners already have it. In terms of the establishment exposure, that's really just taking the propagule pressure at hitting a country's border and weighting it down based on the climate suitability within Australia. So it will be a little bit lower again, because if we think back to the climate suitability model for Australia, it was contracting closer to the coast. Very quickly, we can also use the model to partition the relative risk by different exporters. I won't go into too much detail here other than to say for brown marmorated stink bug, Italy at the moment accounts for about 60% of the risk. Under the worst case scenario, that's likely to decline. But again, as we can see, there's some offset effects going on where other countries such as China, the United States are expected to pick up or increase their relative risk of exporting BMSB to us. We can also do this by commodity type. So these are just the different types of commodity. The one thing I'll just point out here is electronic equipment, EQM, which is the top right panel, is currently accounts for about 38% of the risk introduced into Australia for BMSB. The other output that we get from the model is that not only does the model provide estimates about what's the relative risk coming into Australia, but we can also look at using this model, making the assumption that what we're seeing in terms of contamination rates hitting the Australian border is representative of what other countries experience. We can then also quantify what's the expected propagule pressure or contamination rate hitting different countries' borders, and also what's the the impact of climate suitability on establishment exposure. So these are interactive maps that make it a bit easier to disentangle some of the complexities associated with the model. So coming to the end, what can we use the model for? Well, it can be used for both short-term and long-term policies associated with local border screening assessment. So we can be probably a little bit smarter about how we do our border screening. It can definitely be used for threat prioritization. And it can also be used for thinking about when do we update our import risk assessments. Because if we're changing, if trade patterns are changing, we're importing increasing volumes, and we know something about the propagule pressure for a particular threat we care about hitting that country's border, we can be a bit more strategic about how we do our border screening. We can also directly use the outputs to feed into, say, pest risk mapping. For example, the work that I've done previously for the department, which is now hosted on Biosecurity Commons. And that can also then feed into impact assessment and surveillance design. We can also, coming back to the trade model, we can also use the underlying model for identifying future opportunities as well as the risks to different industry sectors. So it gives us the capability to work out how and where and when should we be adapting to these changes. And lastly, we can use the model for thinking about future extensions, right? So the model is, as Tom pointed out, has a very small subset of damage functions in terms of the underlying trade model at this point, especially those that would impact manufacturing, so the sea level rise. But there's other things that we can do. There's still a bit of uncertainty in terms of the underlying contamination model, so we can add more predictors to the underlying statistical model. So thinking about how long has a pest been present in a big given country, or if we have better estimates of prevalence within a given country. We can expand the model, as Tom pointed out, to not only think about just trade, but also imported changes in human movement, so tourists and returning residents. We can use the model to actually try and simulate global spread and establishment, and then the potential damages that may arise from it. And lastly, we can also use the model for developing a multi-species model by thinking about functional group analysis or using functional traits, morphological or physiological traits within these models. We've also done some work recently to try and validate the model by comparing it to New Zealand. So we've run a similar project for New Zealand using their data and comparing the results. And what we're finding some very, very promising findings where we're actually getting very similar findings in terms of the relative risk associated with different exporters. And I'll leave it there.
Well done. Well done to the both of you. Thank you. And just while we're waiting for everyone, if you would like to put in any questions, feel free to put them in the group chat, or you can pop your hand up if you would like. Just while we're waiting for a few people to put in their questions, just probably to the both of you, like this is some absolutely excellent work. Do we have it? Is it too early, or is it available on the CEBRA website, or is there a way that people can get in contact if they did want to discuss it in more detail or further information? I'm not sure if that's for Tom or James there, or maybe both.
Yeah, Jimmy can take it.
It's in the final stages of endorsement, so I'm assuming it's just a couple of weeks away, and then it'll be made publicly available.
It's doing some free advertising just in case anyone's interested, so they know where to go.
And we're always keen to connect with people. If they want to email us or talk to us about it, that's fine. Just flip us an email. We'll be fine.
Perfect. Throwing it open. Any other questions or anything else that anyone wants to throw in? My chat functionality doesn't appear to be working, so I can't see if there's anything coming through there yet. The only other one, just while we're waiting as well, and I think we did sort of talk about this just towards the end there, James, but if you've got any further thoughts on how advanced forecasting techniques can help anticipate and mitigate trade and biosecurity risks under changing climate conditions.
Yeah, it's a challenging one. So the underlying problem is often we're dealing with rare events, and which is good. We want them to be rare events, and therefore trying to quantify, particularly when you're trying to forecast over time, trying to quantify those rare events with what is relatively a small subset of data that we've actually got. Is problematic. As we continue to collect more data, that becomes a much easier task. But I think the underlying problem now is that the data is still quite messy, particularly if we go down the machine learning algorithm path. It's the old saying is if you can't polish a turd, basically. Right, so it's the quality of the data that goes in, and so it's always going to be a mixture between underlying mechanistic process-based knowledge coupled with what we can do reliably with the statistics or the ML functionalities that we've got.
I think that's a really good point, and you did talk about it just towards the end of your presentation. Those challenges with increasing volumes coming through, various pathways, more demand across the supply chain, data in various qualities does make it a real challenge for anyone, and it doesn't matter how good your AI and ML is. That's a constant sort of battle, isn't it? Any other questions? Oh, sorry, Tom, go for it.
I would just, I wanted to add that we have extended some of the damage functions already. It just couldn't get into 21B. And in particular, people might be interested in the extension we have to 2050 in terms of what's called blue water stress. So this is irrigation water that's going to struggle going forward. We're using what are called WRI, blue water stress indices. And it does generate considerable changes in the results. Australia, which was mildly pink in that global map that I showed, becomes more and more pink because of blue water stress. So what Jimmy and I really want to do is just to start to fill in all of these damage functions in an appropriate way. And we've got a team here who's starting on that, Matthew Cantelli and a couple PhD students. So I would expect there'd be substantial changes going forward, which will make the model richer and more able to predict in a better way. Right.
Good. Yeah, absolutely. I think it's excellent. I love my data science anyway, so it was good seeing all of that work in the background there. But it is a constant challenge, and part of this is also about stronger partnerships. We can't all do it ourselves, so leveraging off experts in the various fields. So I think that's been a really good one. I think you just talked about it before, but just wondering also whether either of you have any other sort of further comments on more on the socio-economic factors interacting with climate change to sort of influence trade and biosecurity dynamics. I mean, any sort of thoughts on that?
Yeah, so I can add in on that. I mean, Matthew Cantelli, our new postdoc, is I think thinking about building what are called SSPs, social economic pathways, so that you can start to track the impacts of changes in population and economic growth by various countries going forward. He's an expert in that area, and we're going to add that in as well. At the moment, the damages are just baseline GDP. What's the impact of heat stress, fall in GDP? But you want to account for the fact that population's changing and GDP is changing by various countries as well. So that's sort of, I think, next cab off the rank for Matthew, and we'll incorporate that into the model. What's nice too is that Matthew is developing for the computational people who are still online, an R wrapper that allows you to solve this model in a fairly reasonable way. We'll do a presentation on that at some point soon, but rather than using the standard GEMPAC or GAMS approaches, you can just run it on a basic server or a laptop if you like, if it's a small dimensional model, using this R wrapper that will incorporate everything that we do in a nice way. So we're going to make it all very, GTAP is usually seen as black box and, oh God, no one knows what's going on. We're going to make it open box now. You're going to have the code, you're going to see what's going on, you're going to see what modules are fitting in, and you'll be able to, make an evaluation and run the model yourself. I think that's really quite exciting. So thanks to Matthew for that, and we'll be talking about that going forward.
No pressure, Matthew. Thank you both. I do note the time, and unless there is anyone else that sort of got their hand up, I think we might wrap it up there. So it was excellent presentation. Thank you very much. We were, I know I was really looking forward to it, and a number of others. We had a really good number of attendees there. For everyone, you can pass on to your colleagues even if they missed it. The recording will be bundled up and readily available shortly after this session, in case they do want to. Oh, look, as soon as I said that, someone's come through with one more question. So I might give you this one, Tom, before we do wrap it up. Normally that does help stimulate everything.
Yeah, so the more I didn't so the statistical representation of this impact on agricultural productivity. There's a new paper, it's probably going to come out in Scientific Reports, that captures all of this. Christine Lee is the lead. It does include CO2, it does include precipitation, it includes heat stress. It's fairly elaborate. So keep an eye out for that. Send us, this is Alan. Yeah, send us an email and we'll flip you that paper and you can have a good look at it. The one I presented on a very quick table was an earlier version of that model. Still fairly nice and robust, but we've done better now going forward. Send me an email. I'll flip it to you.
There you go. All right. That was the last chance. No more questions now. We'll wrap it up. Thank you both for an excellent presentation. Really love these CEBRAnars. And for those that have your diaries out before you head off to lunch, mark in Thursday, 30th of May. That's going to be our next CEBRAnar. And it's going to be featuring evaluating shared responsibility programs. We've got Associate Professor Susie Hester presenting on that one. So should be really good. That'll be Thursday, 30th of May. But I'll just close by saying thank you to everyone for attending. Really appreciate that. Spread the word, let everyone know. And thank you to our two presenters today. Well done, brilliant, and see you soon. Thank you all.
Thanks, Rich. Thanks, everyone. Thanks, Rich.